So as the last talk of this session, it's a pleasure to have Peter Tadic, and he will talk about thermalization of the stress tensor sector.
Thank you. I would like to thank the organizers for the opportunity to speak here, and I will be telling you something about thermalization in large N CFTs. This is based on work in progress with Robin Carson and Andrei Parnachev. So finite temperature conformal field theories are important for several reasons. Some of them are that quantum critical points in a laboratory have finite temperature, and in holography, this type of conformal field theories are dual to black holes and black brains. And therefore, we are going to consider finite temperature conformal field theory on Euclidean manifold S1 times SD minus 1, where beta and R are the radii of thermal circle and spatial sphere. We will consider a large volume limit where the radius of thermal circle is much smaller than the radii of spatial sphere. And we also consider theories with large central charge. We consider these theories in spacetimes where the dimension is greater than 2. So we focus on stress tensor sector of this large M conformal field theories, and the operators in stress tensor sector you can basically construct by having products of stress tensors with some derivatives inserted such that the whole operator is primary, and you can also contract derivatives either between the derivatives or between the stress tensor operators. Here S denotes total spin of your operator, and twist is defined as difference between conformal dimension and spin. And what we really mean by thermalization of stress tensor sector is the following approximate equality. Basically, we equate the thermal one-point function of this multi-stress tensor operators with the free-point function of the stress tensors of these stress tensor operators with two scalar primary operators on the cylinder. And these scalar primary operators have conformal dimension of order central charge. And this conformal dimension is related to the temperature on the left-hand side by considering the case where k is equal to 1, which is stress tensor itself. And equivalently, this thermalization condition can be written in terms of the OP data. Basically, you have to equate the thermal one-point function of the stress tensor of multi-stress tensor operator with the OP coefficients of multi-stress tensor operators with this primary scalar operators. And here this bar denotes that we keep only the leading term in large delta limit of the OP coefficients. Since we are looking at large N or large CT theories, large N factorization really implies that thermal one-point functions of multi-stress tensor operators can be written in terms of thermal one-point function of stress tensors times some coefficients C that are theory independent, and these C coefficients only depend on particular operator that you consider and on tensor structure in the particular multi-stress tensor operator. This is also a schematic way of writing this equality. And now thermalization implies the universality of leading term in large delta limit of multi-stress tensor OP coefficient. And you can see that really from this series of equalities given here. Basically, the first equality is just thermalization condition that we assume to be true. I will show it later that is true. And then the second equality is this large N factorization, while the third equality is thermalization condition, but for the stress tensor itself. And here on the right side, you get this theory independent coefficient C that multiplies the OP coefficient of stress tensor itself. And this OP coefficient is fixed by word identity because the stress tensor is conserved current. Therefore, this right side has to be theory independent. It doesn't depend on the coupling of your theory or something like that. And that really means that this left side also has to be theory independent. And now I'm going to show that in free theory, the stress tensor sector thermalizes. I'm going to show this explicitly. And in that sense, this universality of a large delta limit of multi-stress tensor OP coefficient is actually equivalent to thermalization of multi-stress tensor operators. So I consider a free scalar adjoint model of group SUN on cylinder with central charge given by this formula. And since I consider free theory, I can compute all correlation functions by weak contraction. And we did that for several types of multi-stress tensor operators. And we were computing their free point functions with the operators of the following type. Basically, some of the OP, we compute number of these OP coefficients. Here I have written just some of them. And basically this tk with twist being 2k and spin being 2k are just products of multi-stress tensor operators with no derivatives inserted and no indices contracted. So these operators are operators of minimal twist, while here we have some operators that have higher twist. Basically here you have one contraction of indices, and here you have two contraction of indices in your double stress tensors. And then now you can immediately compare these OP coefficients with one that were computed in holography. Holography is strong coupling, and these OP coefficients were computed in a paper by Fitzpatrick and Huang. And you can see that these OP coefficients are the same in large delta limit, which confirms this whole idea of universality that I just presented you. And on the other hand, you can compute thermal one-point functions of the same multi-stress tensor OP, of the same multi-stress tensors. Basically, these thermal one-point functions can be written in the following form. This is the form that is dictated by symmetry, and the only part of this thermal one-point function that is not dictated by symmetry is this B coefficient. And as I'm analyzing a free theory, I can compute these B coefficients explicitly. And for the same operators as before, I get the following results, basically. And now I just have to assume the thermalization of stress tensor itself in order to relate the conformal dimension of the heavy operator with the temperature 1 over beta. Basically, I assume the validity of this equation. This is thermalization of stress tensor, and I get the following relation between temperature and conformal dimension of the heavy of this scalar primary operator. And using this relation, it is very easy to check that these equations will be true for all these multi-stress tensor operators that I shown you here. Basically, you can check. Basically, this means that all of them will thermalizes, and this equality is the equality between this B factor in thermal one-point functions and the leading term in large delta limit in the OP coefficients. And therefore, all of these operators thermalizes in a sense that I told you. And this thermalization condition is really equivalent to eigenstate thermalization hypothesis for multi-stress tensors. And one should note that not all operators in the spectrum of free theory will thermalize in the following sense. For example, if you consider the operator of the following type, this operator will not thermalize in the following sense. Therefore, this operator do not satisfy the eigenstate thermalization hypothesis, and that's not a big surprise because we don't really expect a free theory to thermalize completely, but we have shown that multi-stress tensor sector, that stress tensor sector of the free theory will thermalize indeed. And I will conclude by saying that stress tensor sector of large and conformal field theory thermalizes for all values of coupling and or for all values of delta gap in the spectrum, including the strong coupling in holographic theories. And leading term in OP coefficients of multi-stress tensors with scalars in large delta limit do not depend on the coupling of the theory, as I showed you. And also stress tensor sector of this large and conformal field theory satisfies the diagonal part of eigenstate thermalization hypothesis. And now one might ask what happens with operators that do not thermalize when the weak coupling in the free theory is introduced, and we expect that these operators are going to get lifted. They're going to get anomalous dimension, and we will not be able to see them in holographic theory. And one can also ask whether this universality of leading term in OP coefficients in large delta limit can be proven by standard conformal bootstrap techniques, and we will give some rough sketch for this proof in our paper, but we are not able to finish it, to prove it completely, because we lack some data that are needed for the full proof via conformal bootstrap. So that's basically all I had to tell you.
Thank you very much, Peter, for the nice seminar. Is there any question for Peter?
Sorry, I see that I didn't turn on my camera until now.